Attention is all you need is a landmark paper from 2017. It was published by Google researchers, and it invented the transformer architecture, right, which was a machine learning breakthrough that's kind of led to our current AI obsessed moment, right? Everything from ChatGPT to Midjourney can be traced directly back to this paper. And I think kind of ironically, the paper authors didn't, at the time, really, they weren't really aware of how big of a deal their research would become. The paper is kind of focused on looking at, research benchmarks and thinking about possible improvements rather than applications. Cool. Folks are saying my audio is a little bit low. Is this better? Let me figure out my levels here. Is this better? Cool. Okay, so a little bit about me. My name's Charlie. Hello. As Rahul mentioned, I was a Stanford computer science grad. That's how the two of us know each other. I was YC S13, and since then, I've been in and around startups for the last decade plus. So much so that I ended up writing a book on them called Unscalable. And currently, when it comes to writing, at least, I'm working on a newsletter, Artificial Ignorance. It's less technical than today's discussion is going to be, but it looks at how we're entering this new AI era and kind of how to get the most out of it, right? So if you find something that I say today interesting or insightful, please, go and subscribe. It's free at ignorance.ai, and I think Rahul has put a link in the chat, so thank you. All right, so let's talk a little bit about today's goals, right? I think there are three things in particular that I want to touch on here. The first is understanding context. So not only what does the paper mean, how does it work, but how is it different from everything that came before, right? I want to talk about the impact. So again, what were the breakthroughs that it led to down the road, right? And how has it shaped this ChatGPT era that we're all now living in? And I want to mention that this is not going to be super focused on the actual nuts and bolts of the implementation. So if you're looking to build ChatGPT from scratch at home, this probably isn't going to be the talk for you, right? That said, there are a lot of really great resources, most of them free, if you want to implement your own version of transformers from scratch. So I am going to oversimplify, I think, a lot of machine learning concepts in digging into this paper. And if you're already a machine learning expert, please kind of just bear with me, right? To start with, I want to do a little bit of kind of neural networks 101, right? Neural networks are systems of computation that we build up from individual components, these building blocks that we call neurons, right? A neuron is a set of inputs that are combined with a set of weights, its own internal bias, and an activation function, right? So inputs get combined with weights and a bias. They go through the activation. Depending on all of those different parameters, it leads to either, in the simplest case, a yes or a no, right? Does it fire? Does it trigger or not? And that output is then fed to another layer of neurons. We use this basic structure to build these gargantuan systems composed of billions, now these days trillions of neurons that decide, whether to update or not, or how to update as they learn, right? So for each training example that a neural network is given, if they get it right or if they get it wrong, we go back and we update those weights to try to get better over time. When it comes to neural networks, there are a lot of different ways that we use them. I think today we're going to be mostly thinking and focusing on language modeling, right? And when we think about language modeling, we're mostly working with vectors and sequences. So again, to oversimplify, a vector is kind of a long list of numbers, right? It can represent arbitrary data. Often it represents a set of probabilities. A sequence is a set of data that is basically, it matters what order it comes in, right? And so that can be, in our case, words in a sentence, right? You could also have it be audio data or time series data, right? That's coming out of a model. And often the model will continue generating the sequence until a stopping point is reached. When we're building neural networks, you can have kind of different inputs and outputs between vectors and sequences. So if you think vector to sequence, right, like data to words, image captioning is one example there, right? So we feed in image data and we wind up with a series of words as the caption. Sequence to vector or text to data is something like sentiment analysis, right? So we feed in a list of words in a movie review, and then we output a probability of what are, is this a happy review? Is this a bad review? So on and so forth, right? And then we also have sequence to sequence, right? Which is something like translation, for example, right? And that's actually the example that the original paper had in mind when it was creating this architecture, right? It was doing something like English to French or English to Spanish. And thinking through that machine translation example will probably help us understand a little bit more of the pieces of the transformer architecture. Before transformers, it's also worth noting there were, I think, a bunch of different kinds of neural networks, right? When it came to especially working with language, we had recurrent neural networks, we had convolutional neural networks, we had long short-term memory networks, right? However, all of these types of architectures had their own limitations, right? First and foremost, I think they were slow. This was mostly due to the fact that they had to be run in sequence. When you were training on a sentence, you had to feed it one word at a time and then go and update your neural network. We got a little bit better at that. We were able to track like hidden states and help that improve the quality of the output, but that just made things slower, right? And since they were sequential, right, they couldn't be leveraged with GPUs, right? These days, everything needs to be parallelizable to take full advantage of the latest and greatest hardware, but these networks couldn't do that, right? And they were forgetful, right? So LSTMs, long short-term memory networks, were kind of the best at this, but even they stopped being effective at about 100 words or so, right? And they were even slower than RNNs. So if you had something like an article, right, that was longer than 100 words, the network couldn't really remember or associate things in the beginning and the end of that article. The key breakthrough, as we were trying to get better at this stuff, was a mechanism called attention, right? And attention is a technique that lets the neural network focus on different parts of the data, right? When it comes to these language models, it is taking one word and trying to understand what are the relationships between this word and the other words in a sentence. How relevant is it? And where do these relationships get created? So if you think about why that's useful, if you're going from an English sentence to a Spanish sentence, the words may not be in the same order, right? So the black cat is, el gato negro, right? Sorry for the bad Spanish. And so those words come out in a different order. And so you're trying to learn, okay, even though it's a different sequence, we're learning the relationships as the words are coming out, right? Now, it's worth pointing out that this paper, Attention is All You Need, didn't invent attention. It had been proposed by other researchers as far back as 2014, but it had always kind of been tried in conjunction with an RNN or an LSTM, right? One of these other kind of less efficient networks. What this paper did was introduce the transformer, right? A type of neural network architecture that used the attention mechanism, but got rid of kind of all the other previous neural network architectures and managed to avoid a lot of their downsides, right? Which is where we get the title, Attention is All You Need. But what does kind of avoiding downsides mean specifically, right? Primarily means they're parallelizable, transformers. They allow sequences of words to be trained on simultaneously. So you're no longer feeding a word, waiting for the update. You're just sending a whole batch of words together and is doing them all at the same time. Right? It means you can train models much faster and much more efficiently. Again, the fact that they're parallelizable means you can scale them up, right? So now that they're more efficient, you can worry less about, okay, will this model train in a reasonable amount of time, and worry more about, okay, what's the biggest data set that we can get to use this, or how many parameters can we pack into this with the latest GPU hardware, right? And in our current era, the state-of-the-art models have billions, if not trillions of parameters. And they were flexible. Other types of neural networks kind of had more rigid requirements when it came to what you could put in and what you could get out. But as we've seen, transformers are actually applicable across a very wide range of different types of data, right? Which is in part what's kind of spurred this explosion of different types of image and audio and video generation, not just text. So let's kind of dive into what actually goes into a transformer. I guess before we get into more of the internals here, it's worth pausing for a minute. I know that was kind of a lot of history, but are there any questions so far? Yeah, Mike, how do I call on you? There we go.
Oh, thank you. Not really a question, more so a comment. I know you didn't want to get too technical, and this isn't a super technical point, but I did want to make a note that the transformers that we see for these generative AI models are actually part of, or actually only parts of this full transformer architecture. I just wanted to make a note of that. I think that's relevant. But I did also actually wanted to ask a quick question. For the parallelization, is it fair to say that that was made possible by the different ways in which the transformer model was looking at the encoding, or the different parts of how a word relates to another?
Yeah, I think that's the attention mechanism, right? That's kind of what really made that parallelization possible. And then the transformer basically said, hey, we can just do this parallelization without having to feed each word in at a time, right? So previously, attention would attempt to learn the relationships, but it did so one word at a time. And the transformer said, let's just give it all of the words at the same time, and it will learn all of them, all the relationships simultaneously. Cool. Vikash?
Hi, Charlie. Hi. Thank you for taking time and explaining this stuff. So I'll just give a quick intro. Like, I'm not a machine learning engineer. I never did anything in machine learning. This is maybe the first talk I'm getting into the machine. I knew about the paper because of the whole AI revolution you were talking about. But yeah, so my question is not very technical. I'm just asking in terms of, you mentioned about few limitations of the previous neural networks like RNN, CNN, and LSTM, like the slow, expensive, and not very long remembrance. The question is, were these limitations recognized after the fact? They were being used for a long time, and connected to that is, do you know limitations for transformers right now? Like what, like in any case, like if there is a limitation and based on new other technologies coming up, transformers cannot be used in that scale or flexibility as it is right now.
Yeah, good questions. So to answer your first question, people were aware of the limitations, right? I think, all of this stuff as it was coming out was considered sort of the cutting edge research, right? There's a reason this was an archive paper and not, part of a Google like product release. And I think researchers were just trying to figure out, okay, what can come next. They knew that RNNs were not good enough for a lot of the applications that they wanted. But, it's sort of in hindsight, the thing that's happened in hindsight is like, we realized, okay, attention was, or transformers were the key to unlocking that next level of performance, right? And even with transformers today, we do know, yes, they are limited. We haven't yet figured out what comes next. I think that's one of the really big questions, in machine learning right now, right? Is what comes after the transformer. To answer your second question, they do have downsides. I do have a slide on that, and so we will get to that a little bit later. But thank you for asking. Yeah, Madhur, am I saying that correctly?
Yep. So yeah, thanks. Again, a naive question. I am not an expert, but is transformers the only way to A, parallelize, and B, like not be forgetful, or it's just the first way that blew up, and we are still discovering more ways?
Yes. So it's kind of the first way that like really was widespread. There are, even at the time of transformers, there were other papers coming out that were exploring other mechanisms for trying to solve these problems, to make things parallelizable and to improve the long-term memory. Transformers, for whatever reason, they were the one that kind of stuck. But we are still trying to figure out, I think, are there other approaches as well, that we can maybe leverage a transformer, and kind of like transformers did to RNNs, what comes next so that we can take what we've learned from transformers and then get rid of some of those downsides as well. All right, so let's dig into the anatomy of a transformer. There's two main pieces that go into this, an encoder and a decoder, right? And so we're gonna kind of step through this diagram here on the left and take a look at what each of those pieces mean, right? When it comes to the encoder, and let's keep in mind, I think, our English to Spanish translation example earlier, right? So that'll kind of helpfully orient you a little bit as we're talking about all these different components. But we start with input embeddings, right? And if you haven't done machine learning, if you don't know what embeddings are, that's fine. They're basically words, a sequence of words converted to numbers, right? That's a pretty big oversimplification, but we convert them to numbers in order, to use them within our machine learning models more easily, in order to do matrix, multiplication on them. And so take words, make them numbers. That's an embedding, right? As we've talked about, transformers went from RNNs, which gave each word sequentially, and RNNs and LSTMs were able to keep track of what was the order of the words coming in order to learn these types of relationships, but transformers don't do that. So we have to add positional encodings because the model needs some way of knowing what was that word's position in the sentence, right? That came with the input. And so we mix that data in with our word list, with our embeddings, and we pass that to an encoder block, right? We actually are creating multiple encoder blocks. That's the N time symbol. And we will end up stacking them and passing through multiple different sets of encoders to keep learning as the model progresses. But each encoder block consists of a multi-headed attention layer, right? So here is kind of where the secret sauce happens. We are creating attention vectors, which are, like we mentioned, the relationships between words in a sentence. And multi-headed basically just means you are keeping track of relationships between one word, right? And then testing multiple different words, right? So if you had a single-headed attention layer, it would basically say, take the current word and track its relationship with one other word. Multi-headed means take the current word and track its relationship with several different other words, right? And then we take a weighted average of all of those different relationships to kind of compress that down to, okay, here's roughly how this word relates to the rest of the sentence, right? We have a feed forward layer after that, right? Which is a fairly standard kind of neural network in machine learning. This basically makes it a little bit easier for the next encoder block to work with the data, right? So it's coming in as this input embedding. We're doing a bunch of transformations on it through attention. And then the feed forward network is kind of like basically modifying that a little bit to pass it to the next block, right? And the add and normalization layers those are steps to basically just help smooth out the machine learning process, right? So as a neural network learns, we're updating all of these weights internally, and the added norm layers basically just help kind of smooth out that process so it's not too jagged as we learn. So that's the encoder, and then we've got the decoder, which is pretty similar, but we've got a few other kind of bells and whistles here, right? Like the encoder, we've got an embedding, right? But this time, instead of the inputs, it's going to be the outputs, right? So what is the sequence of words in the output that we've generated so far, right? So in this case, it might be half of the Spanish sentence that we've started generating. We're also adding another set of positional encodings so that we know where in the sentence each word is. And then we use a masked multi-headed attention layer, right? So the thing that makes this different from the normal attention layer is the fact that we're creating a mask, right? So what does that mean? You figure when the neural network is learning, when you've got the English side, you're trying to learn the relationships between all the different English words in the sentence, right? On the Spanish side, you do also want to learn the relationships between the words in the Spanish sentence. But if your goal is to ultimately predict what is the next word in the sentence, you don't want to give the model all of the possible words in the final sentence, right? It would basically be like giving it the answers to the test and then trying to check, okay, given these 10 words, which one do you think comes next, right? That's not actually very helpful for learning language. Rather, you want to say, given these 5 words, what is the 6th word in the sentence? And you can choose any Spanish word that you know, right? And that's actually what you want to train the model to do. So we have to mask, okay, only the words that we've generated so far, give it to those, and then learn the relationships between those, right? We then have a regular multi-headed attention layer. In this case, you can kind of see from this arrow here, we're piping in the inputs, right? So this is where we start to learn, okay, given the Spanish outputs that we're creating, what is the relationship between Spanish and English? And this is where we can start to learn things like, in the cat example I gave before, the ordering of the words might be swapped around, right? So how are we balancing kind of the order of the words? On the English side, the attention layer also might help you learn things like homophones, right? So if you've got the word, the sentence, the jaguar, ate its meal versus I opened the doors to my jaguar, right? It's going to start to learn semantically that those are different things due to attention. And so we're baking all that in. And then we've got, similar to the inputs, right, our feed forward layers, we've got our add and normalization layers. And then the output here, after we've sent it through all of these decoder blocks, we pass it to a linearization layer, right? So this takes the output from all these decoder blocks and it maps the vector to the final output domain, right? So in this example, it would basically say, cool, we've got this vector of numbers. I need you to change the dimensions of that vector so that it maps to all of the words in the Spanish language that we know, right? So they're the same kind of shape. And then the last step is a softmax layer, which turns the data that we have, the vector, into a bunch of probabilities, right? So it is made it into the shape of all the different Spanish language words, tokens. And then we end by predicting, using those probabilities, we predict the next word or token based on the output, right? And so when we're training it, it'll predict the next token, and then we can say, okay, was that correct or not? And then as we are running it, right, we can use it to predict the next token and have that be the generated output, right? Okay, so that was a lot. I guess there's one other thing to cover, and then we'll stop for questions again. Somebody asked, what's the catch, right? So what are the current downsides of transformers? The biggest one is their compute cost, right? So previously the bottleneck was speed, and we kind of eliminated that, speed and efficiency. But we've now found the next bottleneck is compute, right? Training a state-of-the-art language model today requires staggering amounts of computing power, and only only the kind of the largest or the most well-funded firms are really able to do so, right? If you've been reading the headlines, we're currently in a global GPU shortage, I think in at least some part because of the AI boom, right? And the demand for H100s and A100s out of NVIDIA. They're so computationally expensive because the transformer architecture scales not linearly, but quadratically with kind of the sequences that you're putting in, right? So if you've used ChatGPT, you may understand the concept of like a context window, right? It means how far can the model go? How many tokens can the model remember before it starts forgetting earlier parts of the conversation or earlier parts of the, of the data that it was given. As you train a model to remember longer and longer relationships, the compute required to do that, to manage the attention vectors there, gets squared, right? But like we mentioned, there's ongoing research to try and find the next set of breakthroughs that can bring this cost of compute down. Okay, so that was a lot. I see a couple of questions in the chat. Let's see. John mentioned, what is the source of the arrow going into the output? Yeah, so this comes from basically the inputs, right? So after you've trained on the relationships on the English side, you feed that into the relationships on the Spanish side to help kind of understand the interplay between the two, right? We've got Michael asked, is that probability a number or something more abstract? No, it is actually a number. So I think the softmax layer will turn, it'll turn the data, which may be positive and negative numbers. It squishes it all down into a number between 0 and 1, right? And then we treat that as a probability. Looks like Brenplin, sorry if I'm mispronouncing that. Are you going to explain attention as a technical concept? I guess I missed that one in the chat earlier. Hopefully this explained it as a technical concept. If you have kind of a further question on that, let me know. Cool. Vikash, I think you have re-raised your hand here.
Yeah. Hi. Thanks, Charlie. So just touching on thanks for touching on the downside and the compute cost. So in just technically, if you want to tell, like, I don't understand the paper completely or the transformers completely. So, and coming to the AI compute, the cost is mainly because of the like power usage based on the thing and GPU utilization. Like if you start using GPU, not in terms of like how many jobs are running and how much time is idle, but at the time when a job is running, how much time is idle or something, is the cost because of the power and something else? And are there ways being researched to like increase the utilization, and would that bring the cost down?
Okay, let me see if I understand the question. So is the compute cost due to you're asking, is it due to like the way we're using GPUs? And is it possible to bring that cost down? Do I understand that correctly? No, do we lose?
I think we have to ask him to unmute one more time.
Sorry.
Was that?
Yeah, thanks, Raul. Yeah, that's what I was asking, kind of, yeah.
Okay.
Thank you.
The reason that the compute costs go up is when you're doing the attention blocks, right? You can think of it internally as kind of a matrix. And so you've got, in a simple sentence, you've got like 10 words on one axis and 10 words on the other axis, and you're trying to fill in, okay, what are the relationships? Like how related are all of these different words? As you are working on more and more longer and longer sequences. So as you're trying to get the model to understand relationships between words that are farther and farther apart, you have to make that matrix bigger, right? Now, the good thing about transformers was previously it wasn't a matrix, it was literally one thing at a time, right? So it was just slow and you couldn't do it fast. With transformers, we can say, look, we know how to parallelize these matrix operations, so just plug more GPUs into it, and so we can do that. But now we're hitting a point where it's like, okay, there's only so many GPUs we can get our hands on. And if we
Mhm.
want to build like GPT-5, GPT-6, right, we probably need to figure out how do we do that in a way that's not just, make that that data, that matrix exponentially bigger, because we're probably going to run out of GPU capacity to do that.
So
Hopefully
basically what you're saying, yeah, that answers. Thanks. And so basically, to summarize, you're saying like the number of vector operations you need to do, if there is a way or some kind of, and on the algorithmic side, if the research is being done into do that, getting the same output with less number of operations, or doing those operations with less overhead is the goal here.
Yeah, and hopefully that's kind of the hope,
Got
is we can figure out how do we do those operations in a way that's less computationally expensive in the future.
Got it. Thank you. Thanks, Charlie.
Cool. I see Harsha.
Hi, Charlie. My question is towards, you mentioned about NVIDIA GPUs being in demand to run these AI models. Are there any other GPUs apart from NVIDIA's that we can use as well?
The technical answer is yes, right? And the practical answer is probably a little bit more nuanced. NVIDIA has like really such a level of dominance today, not just because they're creating these GPUs. There are other companies that build GPUs, right? AMD is often kind of the runner up there, right? And there are companies even beyond that. But NVIDIA has such a big lead, not just because of its hardware, but also its software. So they spend a lot of time investing in software tools to help machine learning researchers and engineers run machine learning models and train machine learning models on their hardware more effectively. So you can use different GPUs, but you're sort of stepping outside of this ecosystem that I'm probably not the best person to say it is the best or not, but I can say it is the most widely used. Right?
Okay. And my second question is, are there any papers published on optimizing the transformers right now?
There are a couple that I've seen. I have not dug into them too deeply, but yeah, I would take a look at. Actually, weirdly, Twitter is often actually a pretty good place to find paper discussion, or I guess X now. But there are a couple papers floating out there of people trying, different approaches or trying to improve what's already been built.
Yeah, if you can share those resources, that would be great. Thanks, Charlie.
Sure. Hey, Shivan?
Yeah, thanks for the talk. I had a question about the decoder, especially the feed-forward layer. So there's like a feed-forward layer in the encoder, basically to add the non-linearity, and then there's one in the decoder. Is this do both these feed-forward layers, do they have like the same number of like hidden units, like something like how an autoencoder works? I'm just trying to understand how the actual decoding is happening here. But is this similar to an autoencoder in any way?
I would say so. These models are autoregressive, and the feed forward layers are I think there to my knowledge, right? And in the paper itself, they don't actually give examples of code, right? It's sort of high level architecture discussion. To my knowledge, the feed forward layers don't contain hidden parameters, but I'm probably not the best person to answer that question just from like a technical implementation point of view. It does look like Mike may be able to answer that, though, so I'll let him jump in here.
Thank you very much, Charlie. Before I get to that, though, for the person who asked the previous questions about different papers, you would want to look into quantization and different techniques for scaling down the parameter size of these different models. I believe one paper actually allegedly got the parameters for these models down to like 2 bits at one point. Quip, I believe, is the name of the paper, but usually you'll see quantization around 16-bit. And even in some cases 4-bit integer, which significantly shrinks the size and computational cost of running these models. So you'd want to look into that. That being said, what was the actual other question, Charlie? I kind of zoned out while I was answering that one.
I think it was a question about feed forward layers and understanding. Actually, I'll let Shipman just re-ask the question. Go ahead.
Yeah. So the question was that there's a feed forward layer in the encoder, right? So that you can just add the non-linearity to the outputs of the self-attention model, and then there is a decoder basically to give the representation of the mass multi-head attention, the multi-head attention, right? So I was wondering if this had any sort of similarity to how an autoencoder works, because there's also an encoder and a decoder over there, right? And it's the number of units are sort of the same, because the dimensionality of the input, and you are making it same as the output, just because I know the purpose is different in an autoencoder, but my question was just regarding the feed forward layer. Are you keeping like the units the same or something like that, similar to how the autoencoder works?
I believe structurally it's the same, because I know, for example, that GPT, like the generative pre-transformer models from OpenAI, are essentially autoregressive decoders. And they essentially just take the decoder portion of the transformer architecture presented in this paper and uses that for the generations that are created through models like ChatGPT and GPT-4. So I would imagine I believe autoencoders would be things like BERT, right? Is that what you're referring to? Like the Google BERT architecture?
Yeah, I was thinking more it's just more simply, like, I was just wondering how the feed forward layer was designed. Like, is this like is it just like one layer of units, or is this like an actual feed forward neural network? And if so, is this like similar to like how an autoencoder is designed, that you're trying to keep you're just putting this so that you want the dimensionality of like the encoder output and the decoder output to be the same, and then you're putting it through the softmax to learn for the learning. Is that what you're doing? Like, that's what I was trying to understand.
Pretty much. Yeah, no, you're pretty much correct about that. The feed forward network can be really just any feed forward. Like you'll see with the mixture of experts architecture that Google's been working on lately, that they do kind of switch out multiple feed forward networks as experts within a given model, and that's some of the rumored architectural setup for GPT-4, where they have a mixture of these different feed forward networks to take in the data for the initial input. So the answer is probably, if I'm understanding you correctly, and if I understand autoencoders correctly.
Mm-hmm. And this mixture of experts, is this like using like BERT and stuff, or is just like a separate paper?
It's a separate paper. Like, you want to look up sparse mixture of experts. I know Google did another paper recently that was kind of building upon sparse mixture of experts to better take in input, as opposed to only taking in parts of the input at a given time between each of the different experts. Like, it allows I believe the experts to take like a weighted average of the total input, as opposed to just parts of the input that they kind of spread amongst themselves. I don't remember the name of the paper off the top of my head, but it's very recent, and it's building, like I said, it's just building upon a sparse mixture of experts architecture for, I believe, their autoencoder models.
Sure. Thanks.
So, yeah, I'm sorry, Charlie. I dig into this stuff for funsies, so I didn't mean to take this over.
No. I appreciate it. The goal, my goal here is for folks to learn as much as they can. So by all means.
Thanks.
All right. So I think I'm trying to see if there's anything else in the chat that we mixed. Also, yeah, thank you also, Mike, for answering a bunch of these. So I think we've got most of the questions there. Okay, so I think this last section here, I want to talk a little bit about the legacy of transformers, right? What's happened since. and how did we kind of get from that paper, which was all the way back in 2017, to this current moment, right? The biggest impact was, I think, as we've just been discussing a little bit, all of these models that kind of came down the pipeline after the transformers were introduced, right? In 2018, we had BERT, right, which was mentioned. We had the first version of GPT from OpenAI. In 2019, Meta kind of got into the mix. OpenAI and Google were refining their models, and as you can see, kind of every year after that, it gets a little bit bigger, right? I think in 2023, there's been just hundreds of, fine-tuned as well as kind of new trained models that have kind of been released, right? These are just kind of the ones that have been in the news or have been a little bit more widely known, right? The real turning point, I think, was 2022 for this flood. Google had Palm, and DeepMind working on Chinchilla, and then OpenAI released what became ChatGPT, right? And that sort of opened the floodgates to everything else. And I'm mostly kind of noting that the language models here, but it is also worth mentioning that transformers have impacted image, audio, video generation as well. Stable Diffusion and Midjourney, right, which use diffusion models, are also based on transformer architectures. So, while transformers play a key piece in modern language models like ChatGPT, they aren't the whole story. There are other mechanisms and related papers that go deeper, but I think a kind of a quick overview of what goes into building something like ChatGPT or building a lot of the language models we see today. Data sets, right, as kind of mentioned in the chat already. People say garbage in, garbage out, right? And that's pretty true with language models. It's really important to have not just a lot of training data, but high quality training data, right? Early versions of GPT were trained on forums like Reddit and Stack Overflow, that since expanded to curated data sets like the Pile, which was based on a scrape of the internet. You've got Books 3, which is a collection of books and things like that. And so we're sort of trying to figure out how do we make these data sets better, not just for the initial training, but also for fine tuning, right? So after the transformer network has been trained, you have kind of this engine, but it needs a little bit of, a body around it, right? And so language models are usually fine tuned for a specific purpose. That can be something like having a conversation, generating maybe a specific type of text, or understanding, like how to process instructions given by a human, right? So in its purest form, language models are attempting to complete, a piece of text. So if you give an instruction to a language model, you would be surprised to learn, you might be surprised to learn that it's not going to just follow that instruction and tell you the answer like ChatGPT, right? It's going to assume you're starting a sentence, and it's going to try to finish whatever the rest of your sentence or your paragraph might be. So there's fine tuning. There's also RLHF, which is reinforcement learning from human feedback, right? A technique that OpenAI kind of pioneered. That involves taking a language model after it's been trained and fine tuned, and then actually asking it questions, and using that to steer feedback around, is this a good answer? Is this a bad answer? Anthropic has, with their model Claude, has taken this a couple steps further by not only introducing like some synthetic feedback, so they've got a different AI model that is helping the initial model understand the feedback, but they're also scoring along things like how helpful was this answer? Did it answer the question I posed? And how potentially harmful was the response? Does this have the potential to cause damage or to be destructive at some point? Right. Some other stuff that actually just got mentioned that I didn't put on here. Quantization, right, is a different approach. So once you've got the language model, can you figure out how do we take these weights and turn them into a format that like is not 100% as good, but ideally, like most of the way is good, while using kind of a fraction of the memory cost, right, in order to run that model and do things like that. Or you've got things like LoRa's, which are applicable for image generation, right? Low rank adaptation. It's a process where you're trying to refine the output. So if you think about the image model in general, it can generate any style, but if you really want to fine tune it on like to generate coloring books or to generate anime style, right? You can use a LoRa to very quickly and cheaply modify that model's output. Cool. So a few final takeaways here, right? Transformers, they were a major machine learning breakthrough, right? They leveraged attention and they said, look, we don't need any of the pieces of those other neural networks. We just need attention to understand the relationships between different parts of the input. And they've led to a huge amount of cutting edge models, open source language models, products like ChatGPT, multimodal models we're now seeing with GPT-4, right? But also separate diffusion, image models, audio models, video models, that sort of thing. And one kind of fun fact here, as for the authors of the paper, they've actually all left Google at this point. I'm not sure what that says about Google, but I'm sure it says something. Ashish Vaswani and Nikki Palmer went on to found Adept AI, which was valued at, I think, $1 billion this spring. I'm thinking of Character AI. But they recently left for another startup, Essential AI, which is still sort of in stealth mode. We had the founder of Character AI, now valued at $1 billion. Inceptive, which is actually a biotech company, but has some AI pieces. Lion Jones was the last to leave, founding Sakana AI this summer. We had Cohere, which is another AI unicorn. They're valued at over $2 billion from Aidan Gomez. Lucas Kaiser is a researcher at OpenAI, and Ilya founded Near, which is a blockchain company.